Energy stored in a capacitor. The energy stored in any capacitor is given by formulas most easily derived from the parallel plate capacitor. Consider how much work it would take to move a single electron between two initially uncharged plates. That would take zero work, since initially there's no difference in voltage. And remember, work is change in potential energy, which is Q times delta V. So in the beginning, when there is no voltage difference, there would be no work required to move it. However, to move a second electron to the negative plate requires work to overcome the repulsion from the first electron and to overcome the attraction of the positive plate. The work to move the charges is being done by the battery. The electrons are attracted by the positive terminal of the battery and move through the wire and the battery to arrive on the other plate. Since the electric force is conservative, the work done on this longer path is equal to the work done if the electron just went straight between the plates. So we'll use that as a model. The electrons can't move directly between the plates because the air between them is a very good insulator. To move the last electron from the positive plate to the negative plate requires carrying it through a voltage difference of delta V. The work required to do that is Q times delta V. Since the charge of an electron is negative E, and the difference in potential for the last electron is V, the work to move that electron is equal to Q delta V. So the charge is negative E, delta V is equal to negative V. The negative signs cancel. It's equal to EV, where V is the voltage of the top plate and 0 is the voltage of the bottom plate. If the work to move the first electron is 0 and the work to move the last electron is EV, then the average work for moving all of the electrons is 1/2 EV. This average value is used because the voltage decreases linearly from top to bottom. The work needed to move a total charge Q from one plate to the other is given by this equation, 1/2 Q delta V. That energy is stored in the electric field within the capacitor, and this is one of the functions of a capacitor. It stores energy to be used at a later time. Since the work done is equal to the change in potential energy of the system, the energy stored in a capacitor is given by potential energy here, the energy stored, equals 1/2 Q delta V, where Q is the charge on one plate and delta V is the voltage difference between the plates, and UC is the stored potential energy. The top plate is charged to plus Q, and the bottom plate is charged to negative Q. Charge is conserved as the original plates were neutral. They still add up to 0. Using the equation for capacitance and the equation for electric potential energy in a capacitor, two more expressions for the capacitor potential energy can be derived. So this is the equation we have already, and we can use this equation for capacitance to plug it into here and get two more versions of our equation. So there are three possible equations that relate energy with capacitance, charge, and voltage, but only two of these equations are on the AP Physics 2 equation sheet. This equation does not involve voltage. It's in terms of just charge and capacitance. And it is true, and you can use it. You can derive it if you need to, but it's not on the equation sheet, just this one and that one.